So good afternoon, everyone, and welcome to another afternoon of Das Web, the Data Science and Statistics webinar series. Today, we have the great pleasure of welcoming Afshin Ashote, who is professor at Nova IMS, Nova Information Management School on Universidade Nova de Lisboa in Portugal, where Afshin has been university professor and consultant now for over 25 years. He holds 5 academic degrees, including a PhD in information management with specialization in statistics and econometrics, MBA in finance, and a master degree in mathematical statistics. So we see that it's really at the crossroads of information management and statistics. His research interests indeed center on data science and artificial intelligence, leveraging big data, predictive modeling, statistical learning, and artificial intelligence in risk management. Afshin has been awarded several prizes, including Best Teaching Award in 2023, Best Research Award from the ISI in 2019, and the Scholastic Achievement Award in 2015 from the Central Bank of Portugal. Today, Afshin will talk to us about the data science life cycle, from data to impact. Afshin, thank you very much for having accepted our invitation and for sharing your work with us. It's really a pleasure, and the floor is yours.
Thank you so much. So good afternoon to everyone. And first of all, my thanks to Das Web for inviting me for this talk. And sorry if my voice is not very sharp as it should be, because I was teaching for 6 hours today, so it is a little bit tired voice. So I apologize first for that. I'm going to talk about the data science life cycle from data to impact. And briefly, this is about what transforming raw data in actionable insights and real-world impact using cutting-edge technologies. So more in detail, the talk is about data science and artificial intelligence that are getting importance these days, and using new data sources and technologies for much more complex models. Technologies like large big data, data spaces, MLOps, and recently large language models. In this new atmosphere, professionals need for sure new skills to automate and improve complex systems. And updated knowledge, better methods, and of course, stronger security and legal practices that are necessary and essential for this process to smooth the process. So all of these kind of knowledge and information, they should be gathered to make the new systems that they can work better than what we had before. So in this talk, what I will try to present is a model that combines data science, data engineering, software development, and AI with key technical and soft skills that they are necessary for this kind of system. So the outline would be data science lifecycle, new technologies, and of course, at the end, some examples. So let's start with the concept I call data analytics, hour 230. It begins with data. But not just any data, the good data. Then we use statistics and descriptive analytics to look at past and the data that we have as the historical data and create things like graphs, tables, and some indexes, the average, central indexes. So these kind of things that we call them the information. So with this information combined with analytics and statistical reasoning, we gain usually knowledge, right? So the difference between information and knowledge is that information is something you can see, like data on graph, or something that we can write it down on the paper so we can touch it, it's tangible, while knowledge is the understanding we have in our minds. So knowledge can be different for each person, but information stays the same. So using this knowledge, we make plans, right? So the final goal is to make plan. And today we use machine learning and deep learning to make predictions and forecasts. And the final goal is to find better solution and make better decisions. So the models will give us some insights, and this must be presented as information again. So a kind of tangible thing that we can touch it. And for this, we use nowadays the business intelligence tools to make the dashboard. So these are especially helpful for long-term planning, strategic planning, for helping the policymakers to help the companies. So the outcome is something tangible in also outside of the science to help the process to make better quality. But always we have some, of course, errors also there. In the real world, these kind of errors will happen. So when we act on our plans, the outcomes give us feedback. If it matches our expectations, we think of it as a good action with only a few mistakes or a small errors. We call it in a statistics error, the difference between our expectation with the reality. And we will try it again and again and again, creating a loop in these 230, okay? So we will try to repeat it till this error is not passing the thresholds that we put for our quality. So if the mistakes grow too large, that would be different. We will treat it as a new data, and we start over with all the steps again to make better plans and to revise everything here. So this is how also kids learn, we learn, and how artificial intelligence works. So they try to make this kind of models and try to estimate these kind of errors. And if these errors pass some thresholds, they will repeat to revise the model. But as far as it is like something reasonable, they will keep it like what it is. So the error here, as we could see, is important, and we try to minimize that error. But this might make also another problem. Okay, so there are always errors in our actions, and these errors matter. This is similar to modeling and machine learning approaches. And people who professionally deal with these issues usually come from academia or industry, and both face challenges in managing these kind of errors. They like to have the minimum error, as this minimum error will keep us in that 230 loop, and it will give us the wisdom. But then they make another problem that we call it overfitting. So academics are experts in mathematics, statistics, and computer science. Their models are often very elegant, but sometimes don't match reality. They focus too much on theory and may ignore real-world factors. And, overfitting to their knowledge, something that is coming from the background and whatever is written on the books, but not necessarily fit to whatever is happening outside. On the other hand, we have the industry professionals, right? These industry professionals rely on their experience mostly, and they have the practical knowledge. So the experience and practical knowledge is too much, and they often make good observations. But they may also, similar to what we had in the academia, misuse math or science to support what they really believe. To say that, okay, based on our experience, we know that this is true, so we are looking for some evidence to say that we are right. So overfitting to practical knowledge this time. So what does usually happen? Instead of testing theories properly, they will try to prove their assumptions right and to overfit to their assumptions from both academia and the industry. Academia more on the knowledge, industry more on the experience. So this is the problem of the overfitting, similar to what we have in machine learning algorithms. And both groups tend to overfit understanding. So the solution is what? The solution is to combine these two, to combine whatever we have from the academia with the experience that we have in the industry. And that is what the data science is trying to do, to combine these two and make a good solution that is not overfit to data and experience or the theory, but it could be eligible for working in the real world for the real problems. So that is the role of the data science. So how the data science is doing this? The data science is trying to use the pure sciences first. So the pure sciences that I'm listed here, like statistics, mathematics, and computer science, but of course the other sciences could be also included. So why statistics? Because usually in the real world, we have the stochastic processes. So the statistics is working with probability. And the mathematics, because of the many tools that we have in the tool mathematics, and we can solve the problems. And the computer science, because we are at the age of the technology and the era of technology these days, right? So combination of these two will make some methodology for us, and these methodologies are not the algorithms. We combine them with the data. The data is coming from the real world. The methodology is coming from science. So we prove that this methodology is correct. So we can rely on this methodology, and it could be transformed to some algorithms. And these algorithms, with the combination with the domain knowledge, that is the language of the industry, will make some applications that can be applied. And the object-oriented programming and programmers that will help also these applications to make a kind of final product. And finally, with the domain knowledge, we will try to present this final product and deploy our models in the real world to solve the problems. So this is what the data science is doing, but we can also combine it with the engineering to automate all of these steps that we call it artificial intelligence. So for some of this slide, I have some references here. These are the papers that we wrote related to the concepts that I'm saying. So if you like to know more in details, these are the links and addresses. So let's see how the data science is doing this more in detail. There is always a real target model that we like to know about it. So it is in the real world that we want to discover. But we don't know exactly what it is. Only God knows the true model in the world, right? And we are not God. So that's our problem that we have to solve. And all we have is what? Is some observations that we call it data. And so the observation or data is what? The results we can observe from this real target model. So to understand it, we use tools like mathematics and statistics to build a model that imitate the real one. Our goal is to find some candidate models that produce outcomes as close as possible to real data we observe. Since we candidate models, and these models can't be exactly like the real target model, there is always a gap between them, right? And this gap is what we call error. So this is a kind of distance, right? That this distance in the statistics, we usually call it error. And let's call this error here the standard error or the standard deviation, maybe. That is a distance between our model and the real target model in a very simple way. So it's a kind of average of the error that we might make here. So let's call it here simply a standard error. So we try to find a set of algorithms with the minimum standard error. So this measure will help us to candidate some of the formulas in our mathematical toolbox for this real target model. This set of algorithms has some unknown parameters also, right, that we must estimate. This estimation process also must be accurate to find the best model. But when we estimate, we create another error, right? Another gap from the real target model with what we want to candidate as a model. So as you can see, I draw orthogonal to the standard deviation here. And why are they orthogonal here to between these two distances? In statistics, we know that orthogonality generally in vector spaces means uncorrelated variables, for instance, in regression, right? They have nothing in common or in terms of the shared information, or it means that there is no mutual information between them. So they have zero correlation, something like that. And that is important that here also these two errors that we have, they be orthogonal. So we have this line like this. And let's call this new error as bias. So it is a statistical name for this error that I choose for this part to do the good estimation. So it's very simple description of this. So the total distance from our final model to real target model includes bias and a standard deviation, right? So these two, that would be this distance between the final model and the real target model. So this is a right triangle, right? So the hypotenuse here is the total distance, and it equals to what? The S square of the standard error plus the S square of bias. This means what? This means the variance plus the S square bias. And this is what? This is the mean square error, right? So simply the mean square error, it's the summation of the total error that we might make in this process. And we will try to keep it as a kind of measure to guide us to find the best estimations from the candidate models to find the fact about some that real target model that usually is coming from a stochastic process in the world. Okay, so we want to minimize of this mean square error, and the minimum of this mean square error will suggest a reasonable estimation of parameters for our final model. So that is the process that we follow and to find the model. And if we want to be more accurate about data science complete life cycle, we can see this graphical summary to start from the request that we receive from the markets. So usually this kind of request will be checked with the objectives, the scope, the business values that this request might make for the business. Then we will pass it to the methodology and theories that we have. So whatever we have already as the methodologies and theories from the pure sciences, and if we don't have it, we might like to make it. So this is the activities that we do always at the universities. From this methodology and theories, we will have the methodologies. We will combine it with the good data. Usually we have here the data engineering. So from the data warehouses, from the nowadays from the lake house, we will get the data, and then we will try to make it as a good data to combine it with the methodologies. And then here we have our machine learning and our tools. We have the strategies, and we will send it to the programmers to make some presentation of the models that we built in the previous stage. And then if we make a kind of automation on that, similar to that simple graph that we had before, the graphical summary that we had before, we will have the AI or the artificial intelligence to do it all automatically for us, but it is not the end. As we said before, there is an error always there, and that error must be in a threshold. If it passed those thresholds, we will have the quality management to check the quality of our model, and if it's necessary, we will repeat this process to make the new model with the new characteristics when we are far from whatever is happening in the real world. There might be something happening in the economy, in the finance, so not only inside of the process, but also the outside. So there might be some factors that motivate us to make some corrections. And that would be measured with the errors that we might have evaluated in the quality management, and also some maybe ethical problems that might arise. So this chart is for the data science for finance that is published also in a paper. The address is here. So let's talk about it a little bit more with mathematics and statistics. So usually we have a real target function as a class of functions which generate our observed data. This is our goal to be estimated. But what we can see is only the data that is coming out of that, and we want to know about it, but we must first project it on a small continuous linear space. And why the linear space? Because in linear space we have mathematics and we have tools to solve the problem. So also it should be the continuous linear space, because most of the time we want to minimize the errors. And for that reason, we need to use some mathematical tools. In this case, we want to find the maximum or minimum. So that is the derivatives, right? So we need the continuous linear space to use the derivatives. And that is the reason that we project this kind of function on a small continuous linear space, to have the enough tools in our mathematical toolbox to deal with this with the problem. So with this, we candidate a class of models, and then suppose that we have only 3 parameters. We estimate the error. Let's say that we have the model error and we have this bias here, and our approximation for our parameters that here, imagine we have the theta 1, 2, and 3. And then this distance is important for us to be known, because finally we have to minimize this distance to keep this target model very close to this real target function. So the total bias here for the first parameter would be like this. If we consider it as the 3 parameters, we have 3 parameters here that we will project it on a smaller continuous linear space to be able to use mathematics to solve the problem. So the model error here, the estimation error here, the function with 3 parameters that should be estimated. And this function and this real target function in the real world that is coming from a stochastic process, it includes probability inside, right? So it is like a function that has the probability and has density function. So when we want to keep it close to each other, it's better to not only think about the mean square error or some kind of this kind of simple error measures, but to try to find something to evaluate the distribution of these two and to see that if the distribution of these two is close to each other. So I would suggest the Kullback-Liberal divergence to show us the difference between the probability distribution of our model and the real target. Okay, so KL divergence measures what? It shows actually how much the probability distribution of our model might surprise us when we expect another, right? So we are thinking about the real function in the world, that a stochastic process that is working really in the real world, and we might have another thing. So a kind of measure that show us how much they are matched together. So let's make a blender and put the Kullback-Liberal divergence into our blender as the first gradient that we need. So this is the formula of the Kullback-Liberal divergence for the distance of these two distribution functions. And we can see that it is finally equal to what? To Shannon entropy minus the cross entropy, right? So these two are from this KL divergence formula. So if we look closely, we can see that this Shannon entropy that we have here are both related to what? This Fs star, and this Fs star was what? Something that a stochastic process in the real world that we don't know about it, only God knows. So this is a kind of unknown measure that we have here. But this one is something that maybe we can find a way to calculate it. But this is the measure that finally we have to calculate it. If there is something unknown here, the question is how we can do the calculation or make a measure of the error that works for us for minimizing this error and find the best estimations for our parameters. So let's see how we can deal with this problem and how we can use this Kullback-Liberal divergence as an error measure. So by now we know that the distance that we candidate and the error measure that we candidate to have a better or good estimations for thetas is the Shannon entropy minus the cross entropy, right? So as I said, this is unknown, but the good news is that it is constant. Why? Because that's coming from the real world. That's the function that we want to estimate it. So that is unknown, but that is constant, something that is not changed. So that's an unknown constant. And if we have a measure like a constant minus something, and we want to minimize it, it's only necessary to maximize the second one, the negative one, right? So if we maximize the cross entropy, it would be equal to the minimum distance. That unknown measure is not anymore matter. So that is the good news for us, that we only need to focus on cross entropy. And if we maximize this cross entropy, we will have the minimum distance. So by now we know that the only problem that we have is to maximize this cross entropy, right? And we have to do it based on the formula that we have here. And we know that the x is a random variable, so we cannot use the Riemann integral. This is a random variable in the formula, so we should use a statistic, right? So we should solve it statistically. And in the statistic, we have what? We have a similar formula for average, so we know that this is the expected x as the average, and we have a similar formula as we have here, and it could be equal to xi times probability of xi if we have these measures, okay? So for using these, we know that we have the strong law of large numbers, that x1 to xn, if they be independent with a similar distribution, we can say that if we have enough large sample, the x bar will tend to be mu. So the average, the real average that we are looking for. So this is a kind of estimation that we can use, and we can transform the cross-entropy formula to something like this, okay, that might be that we might be able to estimate it. So by now, we knew that we needed the Kullback-Leibler divergence formula. The strong law of large numbers also will be added to our blender. Okay, so these two by now, and let's see what we have now in our graph. So the measure now is transformed from the minimum distance from the entropy to this formula. So we want to maximize this, and when we maximize the cross entropy, we are effectively maximizing the likelihood. Why? Because cross entropy measures what? How well our models predicted probabilities, and that match to the true probabilities, right? So maximizing cross entropy means adjusting our model to fit the true data distribution as closely as possible. So this is the same idea as maximizing likelihood, right? Finding the parameters that make the observed data most probable under our model. So the concept is very similar. It's like that we are looking for the maximum likelihood when we are talking about this maximum distance or the entropy, the cross entropy that we have here. So the maximum likelihood would be the third thing that I will add to our blender. So by now we are using three theorems to solve our problem. So the maximum cross entropy more or less equal to maximum likelihood, but we don't have this real function, and it is unknown. So that is the problem. And we want to solve this problem with statistics again. And this time with the central limit theorem. That the central limit theorem is saying us that if the number of sample is large enough, then the average of our sample with the bounded variance will tend to be with the normal distribution, with the known standard deviation, and also average, right? So this central limit theorem will help us to find something, a summation for that function that we can use in our formula. So by now we have the formula, we have the cross entropy, and all the parameters that we need to calculate it is known by this maximum likelihood and also with this central limit theorem. So it's not only the cross entropy or the maximum likelihood to be calculated, but also we can calculate the confidence level for cross entropy. That is very important to know that what might be the variation of the cross entropy also. So this is the way that we make it clear that with combination of all these theorems and blend them in our blender, we have a measure like the cross entropy that can help us to make this kind of models. So we use these theorems, and in a continuous and smooth space, we could solve the problem to find the measure and find the good parameters for curve fitting to fit with the real world stochastic processes. So this is a sum up for what I said, okay, that I wrote it in one page some years ago and share it with my students. So this is the sum up of what we said till now. So now we are in the era of technology. So we have the programming languages, we have the TensorFlow, we have the big data platforms like the Databricks and also Spark, the Apache Spark that we use for the big data. We can present our work with Power BI and the dashboard, and we can manage our data sets with not only the traditional databases and data warehouses, but also we have now data lakes, right? And now we have the MLOps that we wrote 2 papers also related to MLOps and how we can apply it for the solving the real problems. So these kind of technologies, they help us to have a better connection between the data providers and data consumers. So this is the way that we get the data, we store the data, and then we try to make some products that the data consumers and data users, they can use it. This is an example of how this kind of things can help in the real world to solve the real problems with combination of different different technologies. So this is a dashboard that I made at the second month of the coronavirus in 2000 when the COVID-19 appeared. So this was based on the web scraping, getting the data from the websites, and then making some models, make some predictions based on the time series, and then try to give some insight about the mortality rate, about the fatality rate, and the different situations in different countries, and how these kind of things are evolved. And also we wrote a paper to show that the official data that were presented at that time was not very accurate. So the error of this data in the official data exposed by some of the organizations, it was not accurate, and we showed that at that time with a measure of the accuracy, and it of course helps to make better data sets after a while. After 8 months, we could make some corrections in the data sets that we received from the different authorities. So that was how traditionally we tried to solve the problems, by using the programming, statistics, computer science, combining the different technologies to solve the problems. And now we have the big data also. And this big data, this is a graphical summary of how the big data evolves by time. So that is also published in one of my papers that is addressed here. And this big data could help us to use the new technologies and to combine whatever might come from the non-traditional data sets to help our models to perform better. But again, the big data is not the matter, the good data is important, right? Because the data that we can get from the big data sources, they might also increase the noise, and that might make some problems for our models not to actually help us, okay? But we have the parallel computing, as you can see here. This is one of the projects that we did. So the parallel computing for getting the advantage of the computational power and of different computers, then solve the complex problems better. So it gives us this facility and the instrument to do what? To make much more complex models rather than what we had before. So what we could do was to make the complex models with the ensemble model. So we could combine the different models by using the big data, by using the computational power that nowadays we have, by using the deep learning. And we introduced a model for time series modeling that we call it LLMs. And it was based on what? Based on the layer learning and the ensemble learning strategies. So by combining the two strategies and make the time series models smart somehow, or intelligent somehow, that they can choose the best model to combine, not only to combine the fixed models and then try to improve the estimation, but also to be smart enough to choose between the different models that we have. That was what the LLMs was doing. And also to use the panel data sets with the huge data. So the big data also platforms was used here to ingest the data into our model. And that was something more advanced than what we had before, right? That we use it for estimating the excess mortality for the COVID-19. as that was a problem that we tried to solve in WHO. So that was kind of a new model to help us to estimate something that we don't know about it, because the excess mortality is talking about the mortality that we don't know. We don't have data related to that. So that's a very important problem. That is like doing a magic, because when we don't have data, we don't know what to do, but we have to use this kind of technologies. We can do it, and to make some new models to solve this kind of problems. So you can see here, this was all the methodology that we used to solve this kind of problems. These are the databases of the World Health Organization, the WHO, and this is the invented model that I did 2 or 3 years ago to make it more complex. And this complexity that you can see here was possible with what? With the computational power, the additional computational power that we have, with the new big data that we have, and also the technologies and combination of the different modeling approaches. So beside of this big data and all models that we had from statistics traditionally, now we have the deep learning and the large language models. And this deep learning, as you can see here, and this is a reference for the forward and backward propagation that I explained it completely in this video. So we try to make more complex models also in the deep learning models, and this kind of new approaches will make new LLMs, okay, like the ChatGPT or the others, to solve the problems better, or to use the technology, the computer science, the statistics, mathematics, and all the things, all the complexity that you can see in this picture, to give us the more smart models, more intelligence, and to make us able to solve the problems better, to make the better decisions. So that is what the technology is trying to do by the help of mathematics and statistics, and also present something valuable for the domain knowledges and for industry. So this is the architecture of generative pre-trained transformer, GPT, the foundations of the LLMs like ChatGPT. And as we can see, unlike the older models that processes words one by one, here we have transformers, right? And the transformers use what? The attention mechanisms to analyze entire sequence at once, okay? To not look at each word individually, but to make a picture of whatever is happening there. So it could understand the complex relationship between words. It can generate the responses, and it can predict something like the language that we use daily, okay? So that is something that is happening by combining all of these technologies that we talked about it. So now we are using this kind of technologies, the LLMs, and also the AI agents to solve a problem. This is a project that I have now for Statistics Portugal, for INE. So to apply this kind of technologies with the LLMs and with the AI agents to make the safe rooms completely automatic, and for giving this facility to researchers that they need the official data to not anymore presented in the safe rooms physically inside the Statistics Portugal to analyze the data. So how we can use this kind of technology to make some virtual safe rooms that the people, they can connect to the databases of the INE or the official statistics databases. And using this kind of technology, we can give them the access to data in a safe manner with all all the problems that might arise for the data sets, for the safety of the data set, and to make a safe relation between the researchers with the databases that we have inside the statistics portal. So the private information is a matter here. The output checking is important to be done here. Nowadays, it is done by some professionals at the statistics protocol, but we are using now the machine learning and AI agents with using the local LLMs, the large language models, to do the similar job and to make it much faster, and at the same time maybe safer. Okay, so that's the goal that we are looking for, and we are doing this now, and this is the ongoing project with all of this new technology. So here we have the databases, data warehouses, big data, the AI agents, the large language models, and the deep learning. So all of this, they should be combined to make a system that works good enough to fulfill all the things that we have for the to make this virtual safe rooms for researchers to get the data. So that was all for my talk. We have a data science discussion group that I put the address here. And also we have the data science YouTube channel that the address is also available here. And some of the support materials and some of the things that I already discussed here in more details, they can be accessible in these two resources. So feel free to take a look at this too. And thank you for listening. I'm open to the questions or maybe some remarks. Thank you.
Thank you.